We're going to talk about the second type of mole calculation. And you're going to notice that I have Avogadro's number written at the top here. And notice that the number, we just keep it to 6.022 times 10 to the 23. This could be cookies per mole, atoms per mole, molecules per mole, whatever number of substance you have where you're counting particles, we put that per mole of a substance. Notice that we have a second mole triangle here, and what that would look like in terms of variables, we let the letter N mean mole, and then on the top, we would have number of particles or number of molecules or number of atoms. That goes on the top. And on the bottom, we have Avogadro's number, which is written as capital N with a lower subscript capital A. Now, this formula here, not a big fan of because there's so many N's involved, but hopefully you can learn to keep that straight in your head by learning what each of those symbols represents. So in this particular question, they're asking you for how many molecules of magnesium chloride are in a 0.789 mole sample. So in this scenario, they're asking you for number of molecules. So that is our unknown. They give us moles, so that is our letter N. So our letter N represents 0.789 moles. And we always will know Avogadro's number. We always know that. That's just a number that we have to memorize. Okay? So if I had to solve for number of molecules, that's this symbol here, we would have to rearrange this to isolate number of molecules as a single variable on the top, and we leave it as a numerator. So if I was to bring Avogadro's number to the other side of the equal sign, instead of being divided, it would be multiplied. You can use this mole triangle if you were trying to solve for number of particles. This is a variable that you are trying to find, so you would cover that up, and then you would notice that these two are side by side. So in the mole triangle, the variables that are side by side, you always multiply, and if they're on one on top of the other, you would divide. So in this case, when I rearrange, number of molecules equals moles times Avogadro's number. And now I can substitute my values in. 0.789 moles times 6.022 times 10 to the 23. Now, because this is a molecule, I write down molecules per mole. And what I notice in this scenario is that my moles will cancel out because I have one unit that is in the numerator, one in the denominator, and then I go ahead and I put this into my calculator. Now, in putting this in my calculator, to enter in Avogadro's number, which I'll put first, 6.022, I use my EXP button, and that already gives me the times 10, so I don't put times 10, that EXP button does that for me, 23. So there it is there. I will multiply that by 0.789, and I get this big number, 4.751358. Notice that space means times 10 to the 23. How many significant digits am I going to report to? Well, I take a look at my original question, and I notice that there are 3 significant digits. Remember that any zero that is preceding a decimal is just a placeholder. So we have 3 significant digits. So my answer will be 4.75 times, now remember that's what that space means, 10 to the 23. If you just wrote 4.75 and you forgot the times 10 to the 23, that doesn't make sense because this is roughly 5 molecules, but this value is really 4.75 trillion billion molecules. So it's really important that you keep that exponent there, and we really should have our unit of molecules. So when you have a 0.789 mole sample of magnesium chloride, this is how many molecules would be in that sample. Down below, it's asking you to count how many atoms of magnesium and how many atoms of chlorine are in the above sample. Well, when I take a look at one single molecule of magnesium chloride and I look at the subscripts, I would say that you have 1 magnesium and you have 2 chlorine. Now, what if I was to put a 20 in front? You have 20 molecules of magnesium chloride. How many atoms of magnesium would you have? Well, in this scenario, you would just take your coefficient and you would say, oh, I have 20 magnesium atoms and I have 40 chlorine atoms. What if I was to put a 100 in front? Well, you would have 100 magnesium and you would have 200 chlorine. What if I was to put 4.75 times 10 to the 23? So 4.75 trillion billion molecules of magnesium chloride. How many magnesium atoms would you have? So in this case, what you would do is you would do exactly what you did before when you were working with numbers that didn't have any exponents. You would have 4.75 times 10 to the 23 magnesium atoms, and you would have 2 times that value. So you would have 9.50 approximately times 10 to the 23 chlorine atoms. So that's how we figure out how many atoms we have in the above sample. Let's take a look at a multifaceted question that's going to involve both mole calculations. So what I might do up at the top, I might just write down those 2 calculations on how to solve for moles. And I'm going to refer to those as needed. It's asking, what is the mass of 5.67 times 10 to the 24 molecules of cobalt-2 chloride? So it's asking me for mass, so that's letter M. That is my question mark. They give me number of molecules, so that's NO, number of something. So 5.67 times 10 to the 24. Cobalt-2 chloride, okay, is CoCl2. Now what I would need is I would need to use my periodic table to determine the molar mass of cobalt-2 chloride. So what I would do is I would go to my periodic table and I would click on that and I would say, okay, cobalt has a molar mass of 58.933. So I just might write that down, 58.933. And chlorine is 35.453. 35.453. There we go. So what I would do now is figure out my molar mass for that. So I've got 1 cobalt, which is 58.933. And I'm going to add that to, I'm going to use my square bracket, 2 times 35.453, close my bracket. And the molar mass of cobalt-2 chloride is 129.839. grams per mole. Okay, so this is all the information that I have right now. My target equation. In order to solve for mass, I look at mole calculation number 1. It's the only formula that has mass in it. So if I rearrange this formula, I would keep mass where it is. I bring molar mass to the other side of the equal sign. And so my formula would be mass equals moles times molar mass. Now, if you needed to use your mole triangle, this was the first mole triangle that we had to figure out the formula for mass. What you do is you isolate the mass, the variable that you want. You see that it's moles times molar mass. So that is a way that you can get that as well. I know that I have molar mass right here. What I don't have is moles. I'm given number of molecules. I cannot just go ahead and put that in the place of moles. I have to go to mole calculation number 2. and I have to solve for moles. So what I'm going to do is I'm going to take my number of molecules. I'm going to enter it into my calculator. So there's my number of molecules. And I'm going to divide by Avogadro's number. And this is molecules per mole. Okay, so what's going to happen is my number of molecules are going to cancel out. Now let's see how I enter this on my calculator. Okay, so let's see if I can get that into focus so that you can see what I'm doing. All right, so I'm going to enter in 5.67 exp, which means exponent 24. I'm going to divide. Now I always put anything that has an exponent in brackets. So I'm going to use my bracket key. 6.022 exponent 23, close bracket, equals. So I get an answer of 9.41547, blah, blah, blah. How many digits am I going to report to? Well, I go back to my original question and I see that I have 3 significant digits. So I will keep my answer to 3 significant digits, which then gives me an answer of 9.42. My units will be moles. Not done yet. The original question was asking, what mass do you have of cobalt 2 chloride when you have that many molecules? So now I have enough information. I can plug in my mole value, 9.42 moles, times my molar mass, which I solved earlier, 129.839 grams per mole. And I already have this actually in my calculator. I didn't clear it, so I'll just leave it there with all of those digits. I really shouldn't be rounding too early in my calculation anyway, so it's best to leave all of those there. Multiply by 129.839, and my final answer I have is 1,222.5 grams. Now, technically, because I'm only supposed to be reporting my answer to 3 significant digits, the way that you would report this is you would move this decimal 1, 2, 3. You move it in between the first 2 digits, and you would report this as 1.22 times 10 to the 3 grams. So this would be your final answer in what we refer to as scientific notation, because I can only report my answer to 3 significant digits. This would be too many.